everyone, I'm Ed Liu, and yeah, my talk today is about the latest research iteration from the DLSS technology family, which is Ray Reconstruction. And Ray Reconstruction is basically an AI model that's trained specifically for improving the image quality for real-time ray trace games. And it does it by unifying the reconstruction process, namely all the denoising process and the super res process that's been commonly used in all ray trace games. And we'll talk about why this is beneficial in the later part of the talk. So this is the brief agenda. I'll start with a high-level overview of what Ray Reconstruction is, what it does, where it's available, and so on, and why it makes sense. And then I'll try to provide an intuitive explanation of why denoising for real-time ray tracing is such a hard problem. In fact, I noticed all the posters back there are about denoising. And finally, I'll end the presentation with a short description of how to integrate Ray Reconstruction into your product. Okay, so we introduced DLSS 3 along with our Ada architecture launch. Basically, combining frame generation and super resolution, we now actually already live in an age where 7 out of 8 pixels that you see, the gamers see on screen, are actually generated or reconstructed by AI models. And super res basically quadruples the resolution, and then frame generation actually doubles the frame rate. And then, so this type of performance breakthrough is I think, one of the big important reasons that we can actually enjoy path trace games at 120 FPS on today's hardware, because otherwise it simply is too taxing. So another really pivotal advancement for real-time rendering, in my opinion, in the last 5 years is real-time ray tracing. And image reconstruction has been playing a very critical role for real-time ray tracing from day one. As we all know, we only have the such limited budget to perform really sparse ray sampling with the real-time frame rate. And so a typical reconstruction pipeline for ray trace game today kind of look like this. So the game engine would render a set of geometry buffers and textures and materials and so on. And then a set of rays will be shot starting from these buffers, and from that process we'll get a set of noisy radiance buffer, color buffers containing things like reflections, AOs, or path trace GIs, and so on. And then denoisers are then run on top of each of those buffers. And typically these denoisers are designed specifically for the type of signal that they are designed for. For example, reflection denoisers take into account information like roughness or hit distance and so on. And then an indirect diffuse denoiser might take into information like normals, etc. And these denoise results are then later combined into an alias buffer, but noise-free. And of course, at the very end of the pipeline, there is TAA that'll remove the final, all the aliasing in your image. So what the users see will be noise-free, aliasing-free, and it's just smooth, temporally stable, and so on. However, with the introduction of DLSS 2.0, upscaling has since become really ubiquitous in the industry. Everybody's doing that. And the benefit's obvious, right? Because it's running path tracing at 4K on today's hardware is simply too expensive. So with DLSS 2, the pipeline also kind of changed like this. We now have upscaling at the end. And so basically the upscaler, instead of like TA reconstructing image at the same resolution, it'll stretch it to some high resolution, typically at most 4x, sometimes 9x in the case of 8K. However, like using upscaler in the ray tracing reconstruction pipeline is actually less straightforward than one might think. The most critical limitation from this is that all these upscalers, they require an accurate viewport jitter offset for them to work. For them to function, for them to actually be able to accurately reconstruct the high resolution image at the end by knowing where where the low resolution sample comes from. But since denoisers themselves are actually temporal and spatial filters, just kind of like an upscaler, the temporal filtering process actually removed the subpixel jitter offset, which makes the downstream upscaler fail to perform its task. And this screenshot actually took from one of Digital Foundry's video. Basically, on the left side, we have like a DLSS performance mode at 4K running ray trace reflections. And on the right side is native rendering, basically native ray tracing plus TAA. So you can see textures and geometries are, that seam is like accurately reconstructed because, denoisers don't mess up with them. But then the shading, the thing that's also really important visually, gets kind of a blurrier. So other than these, the heuristic that's from, like I said, denoisers also similarly to upscaler, they're temporal spatial upscalers, temporal spatial filters. The heuristic used in the denoiser can often also kind of fight with the upscalers. Like one good example is that the denoiser often, the denoiser sometimes will produce low frequency, blobby, and even temporarily low frequency boiling output, whereas TAA is really designed, or upscalers, they're designed to get rid of pixel size shimmering. And these conflict will make the end result sometimes contain, some of the artifact from denoisers will leak through the upscaler. So it's important to basically think about the reconstruction pipeline in the ray trace game from a global point of view. And that's one of the strongest motivation that for us to develop ray reconstruction, because we all want our ray trace game to look good, even with the presence of upscaler, which is very, very common. And so what ray reconstruction does is that it changes the pipeline. You notice that, compared with the previous pipeline, the denoisers are now removed. And also, so instead of running the denoiser, we now simply composite all the noisy color buffers together into, without denoising them. So now we get the input to ray reconstruction is low resolution, is aliased, it's also noisy. And then basically the ray reconstruction will take this type of input and just give you the high resolution, aliasing free, and it's smooth on the outside. And because this, the ray reconstruction model does it end to end in a way, kind of using AI models, all the information that it needs to perform both denoising and upscaling are present, so that we get properly reconstructed high-resolution signals. And also notice that ray reconstruction actually removes all the denoisers. So whenever your existing denoisers in your games are really expensive, you also get some performance benefit as well. Just some quick example of the type of input that we could use it for. This is 540p, 1SPP, ray trace shadows, reflections, AOs, and the output could look like this. It's high resolution 1080p, and then it's smooth. The reflection is properly reconstructed. Another example, 540p ray tracing, and then after the reconstruction. Another one, this is actually path tracing from Cyberpunk 2077, and I'll just want to point out that this is the input, this is the output. I want to highlight that it's doing the denoising of it has to get rid of all the really challenging noise in this region, which is completely indirectly lit, and also in this region it's much less challenging. But you notice there are actually also moire patterns on this on the sidewalk here that it has to just while doing denoising it has to remove moire patterns, and also it has to while aggressively filtering out the noise, it has to also learn to basically keep the details of things like these neon signs. And this is another video example. This is a long video, I'll just skip ahead a little bit. See if I can do that. Oh, I'll just let it play. Yeah, this is Omniverse, and it has global illumination, ray trace reflections, AO, direct lighting, and so on. And it's later you'll see that it's stable. It's also smooth, and later when I move the light source, you'll see that the lag is also very limited. Yeah, basically, I think for any denoiser, there's this trade-off between stability and lagginess. And in this case, it's a primarily indirectly lit scene, and it's quite impressive. Like they can be both kind of stable and responsive at the same time. So basically now with the addition of ray reconstruction to the DLSS family, AI is now reconstructing pixels, frames, and now rays. So we're pretty excited about this. And just playing one more slide from our marketings. We deployed this in a couple games already, and in Cyberpunk we're getting the best image quality and also the best performance using this approach. You'll notice that in the DLSS 3.5 case, that's the only one that's that actually has a responsive lighting, because all the other one, in order to make sure the image is stable, there's some lagginess in the lighting doesn't update as responsively. So yeah, I guess since its launch, it's been kind of pretty well received generally by the press, and we're pretty excited about this as well. And it's now available in these 4 games and some renders, and more games will come later. Yeah, I do want to point out specifically that it also works with Lumen in UE5. The shadows and reflections can benefit from this. Okay, so in the next section, I'll try to provide a high-level overview, like why is this such a hard problem that it actually justifies deploying an AI model for this. So why is denoising so hard? I think one of the big reasons is that the input signal to noise ratio in the input buffer can be just extremely wide. On one hand, we have path trace global illumination. If your scene is indirectly lit from a small keyhole behind, an emissive object behind a small keyhole, then really the problem is intractable. And on the other hand, we also have direct lighting signals, RTX-DI, reflections, a shadow, etc. Those are actually easier to denoise. And it's pretty obvious that the optimal denoising approach for those will be slightly different. Even if you use the same algorithm, the parameter will be different. But those can actually perfectly coexist in a single title or even a single game. Just as one example, this is 540p. This is 1 path trace GI. I guess you can really barely make out what's going on in there. So at 8,000 SPP, you can see what's happening. But even in this case, at 8,000 SPP, it's still pretty grainy. And this example shows, on the other hand, if you only have ray trace effects, in this case, like shadows, reflections, skylight, and AO, it's much easier to handle. Another really challenging thing that we have to be aware is that the signals can be highly dynamic. We have things like moving shadows, we have moving light sources, or moving objects that are constantly casting, making the lighting change. You can also even just have flashlights. That basically these things will prevent the denoiser from more aggressively spatial reuse, and which in turn could lead to boiling or temporal artifact. Again, denoisers are really a large collection of tricks that are really brilliant. And the way it works is filter with large footprint whenever it can, and aggressively temporal use whenever it can. And one of the such really obvious heuristic is temporal reuse. People reuse little when the pixel is newly discluded because there's no valid history information for it to reuse, and people reuse a lot whenever there is whenever the pixel has been valid on screen for a long time, and people design heuristics to basically achieve this. And we also generally try to adapt our spatial filter kernels based on the type of signals that we're denoising. Some algorithm uses variance, some others leverage specific information from the signals. Like, for example, spherical harmonic space denoising has been quite commonly used in both NRD and also Lumen, just because it's a better way to preserve normal detail for denoising your global illumination. And specular reprojections, the motion vectors can be specifically calculated for reflection, as those are moved differently from the primary surfaces. And basically, light source sizes in a distance light source can also, it makes sense for it to use when your denoiser is for shadows. But I just want to mention that just because it's really a ton of tricks, with a ton of tricks and a ton of heuristics, it comes with really a million knobs that controls the various aspects of these spatial temporal filters. And it's very common for, before we ship a denoiser in games, some expert who either developed the denoiser or developed the game has to go in and spend a couple weeks to tune the denoiser. They sometimes tune the hyperparameter, they sometimes reinvent some new tricks on the fly, or sometimes they just modify the game engine a little bit more to work better with what they have. And the end goal is to ship the game. And even then, the final ship quality is like I would say it's like a best balance point among all these artifacts. All these artifacts that still somewhat exist, but it's been tuned to not look visually off-putting and to be tuned to make visually plausible. And just as this, I put a loop here to just kind of provide one maybe a high-level example of what could happen. You know, if your image is ghosting, you tweak your temporal filter to make it more responsive, and then that leads to instability, maybe especially in some area where the geometric extends, where you cannot use large spatial filters. So you kind of try to decrease your spatial filter reuse, then your other part of the image will become grainy and under-filtered. So you try to increase your spatial reuse, then your image could become now over-blurred. So you try to decrease spatial reuse and now increase temporal reuse, now your image becomes ghosting again. So just, you know, the things are you know, actually happening for people who's working on denoisers. It's maybe a little bit exaggerated, but again, the final goal typically is to achieve a good balance among all these things. So just as one example, this is Unreal with RTX DI, reflections, and AO shadows. I'm trying to compare the handcrafted denoiser versus the Ray Reconstruction. So whenever you see there's shimmering in the grass, that's the handcrafted denoiser. And just because in this case they have to make sure the dynamic lighting and the reflections and the shadows are responsive. Like they could change to make the shadows not as grainy or not as flickery, but then the shadows will become not as responsive. But you know, Ray Reconstruction as an AI model really gets the best of both worlds in this case. And another example, you know, it's pretty obvious to see that the Ray Reconstruction results, the shadow is just more responsive. And on the other hand, in this case, the shadow is like more laggy. But again, if you try to make the shadow more responsive, then you'll start to see graininess and shimmeriness in some other part of the image. Another very important fact that I think is more often than not overlooked is that ground truth level quality is just very difficult to achieve with real-time denoisers. And we all love the ground truth quality that we see from movies or you know, Pixar animations and so on. And this is not intentional, but like I said, whoever has been working on or tuning this denoiser for game, their primary goal is they try to ship the game, and they try to achieve a balanced look that is plausible and artifact-free. So even they more often than not, they do use ground truth as the reference when they tune the denoiser, but it's not the primary goal to match that look. For example, over blur is a common problem. It can be usually seen in contact shadows that just often get neglected, and also, you know, object will just look less grounded if the contact shadow gets over blurred, and that's really common. And it's also seen in reflections. Reflection will be less detailed. You know, this is a case that's kind of demonstrating the contact shadow problem. The upper image is the handcrafted denoisers, and the lower image is the AI model Ray Reconstruction. It's really not a problem for AI model like Ray Reconstruction because it's, you know, we don't really know how we achieved it. We just trained it with really high quality data that's been, you know, that looks really premium, that has all the correct lighting. And I'm not saying that a Ray Reconstruction like solved path tracing, but in generally it gets a closer perceptual feel in the output to the ground truth, and that's a lot of reason why people sometimes think that, you know, it just looks better in different ways. This is another example in reflections. On the left is the handcrafted denoiser, on the right is the Ray Reconstruction. And in this case, the reason that the Ray Reconstruction is sharper and more detailed is twofold. The first is that the denoiser, like I said, it often just over blur. It's not been the primary goal for it to just look really sharp. Instead is for it to make look plausible and artifact free. And the denoiser is over blurring. And even if the denoiser is not over blurring, it'll you know, if somebody tuned a perfect denoiser for this, in this case, when it's working with the upscaler, it'll come with the limitation that I mentioned at the very beginning, which is the subpixel jitter will get removed by the spatial temporal filter, and then the upscaler will fail to properly stretch it to a higher resolution. Another AB from where Ray Reconstruction is producing just superior and more detailed lighting where the geometric is dense. You can look at the, you know, just look at pretty much all the trees in the stairs. We have more. This is, I guess, another form of contact shadow that's been quite hard to get right with handcrafted denoisers. Yeah, this is another AB example. So in this case, I guess I want to say that before you look at the Ray reconstruction result, this image looks perfectly fine. It's really smooth. It's also path tracing, and the geometric, everything looks plausible and detailed. But it's until you switch to something that's like, that's even more detailed, you notice what are you missing. Like maybe I want to highlight some of the metal craft on the top of the image, how the AI model it's actually showing it's actually showing more geometry. So in this particular case, I guess we can confidently claim that this looks better than native rendering, because even if you don't run the upscaler, you just run your ray tracing at full resolution, you still will lose these details just because lighting wasn't reconstructed properly. Yeah, I think this is my final example from Omniverse. Let me toggle back and forth again. It's similar to before. Before looking at the better image from AI models, this image looks just fine. And but it's because when a denoiser messed up, it's not like when upscaler messed up, everything is like now low resolution. It's still sharp and nice, but you just don't know. You're actually missing a ton of like material. Those seams on the floor, those are just missing, and also the tiny shadows on the tiny thin shadows from the tire on the left is also missing. Yeah, I hope I get the point across. All right, I'll conclude with some high-level fact about how to integrating this thing, Ray Reconstruction. So these are the input buffers that Ray Reconstruction takes. If your app, your engine already supports DLSS super resolution, then the first three buffer is actually the same. It's just the input color buffer, the motion vectors, and the depth. Also, of course, there's the viewport jitter, which is not a buffer, but you have to pass it to it. And Ray Reconstruction needs that too. And all the other geometry buffer down there is the new ones that's required by Ray Reconstruction. And in particular, these two things, the specular hit distance and the view matrices, are optional. If you don't pass it to it, if your app is not that noisy, it does not have a ton of reflections, you don't have to pass it to Ray Reconstruction, it'll still work. But if you expect your reflection is really hard to denoise, passing these two things will allow the Ray Reconstruction to reconstruct the specular reflection motion vectors and use it to help the specular reconstruction. So for the supported signal type, it's pretty an agnostic model, so it supports pretty much everything, from the simple things to ray tracing to the most advanced register or path tracing or world space caching, what have you. The model is kind of trained just to take noisy signals and to remove the noise while maintaining the details, I guess. And but there is some kind of a tricky requirement on the signal itself. One of the big things is that the signal must be random. Like what is not random? A good example is checkerboard rendering. If a lot of the engine does this. If some engine, the shoot rays in the checkerboard pattern so that it is to save some performance, this will not work with Ray Reconstruction because we find it hard to train it to make it work. So it's advised you at least replace your checkerboard pattern with 1:2 random stratified sampling, so that there's not a fixed pattern to confuse the model. Another thing is that sometimes there is also a screen percentage option for ray tracing. Sometimes they trace reflections or GI at a lower resolution, and before they feed to the denoiser, they simply stretch it with some bilinear upsampling. That'll also not work. The model expect the input noise is pixel sized. So in this case, we either do a sparse upsampling or just do a random. Instead of just really reduce the screen percentage, just replace it with random sparse sampling on a larger buffer. Yeah, and then sometimes the spatial and temporal reuse from register can also cause the correlation, which could confuse the denoiser. So in the games that we shipped, we can also tweak the spatial and temporal reuse component from register to be as randomized as possible. Yeah, of course, this is still just a denoiser. If your scene is like really crazy difficult, it won't work. So try to reduce make sure your signal is high quality as possible before denoising it is advised. For example, you can use something for path trace GI. You can use something like either world space caching or register to help it. For other things like reflections and shadows and and AO, I do expect those to just work. unless you really reduce the rate budget. Some other important note is that the algorithm, similar to super resolution, it has to be integrated before all the screen space filters. So if you have depth of field or motion blur applied on your noise and smeared up, the model won't be able to handle it. Another thing that we also commonly have to solve in the game that we ship is screen space subsurface scattering. We also have to change those kernels to be more stochastic so that it doesn't confuse the model. All right, with that, that concludes my talk. And ready for questions and comments.
Thank you. Thank you, everyone. So maybe, is anybody who has questions? Okay, so I have a question. So, whack-a-mole example, your slide was whack-a-mole. So maybe just whack-a-mole. It looks quite interesting. So maybe, is that a still open problem, or is some DLSS 3.5 already solved that problem or something like that?
I would say it's. You mean does 3.5 has that problem?
Yeah. So maybe.
Yeah, we have, I guess, different problem because the 3.5 is an AI model, so it's like a black box. It just doesn't provide a ton of knobs for you to control it. But whenever artifact happen, we could still tweak the ray tracing part to make it work better with this, or we just retrain the model. So I guess the tweaking kind of happened in the training side because there are data, there are laws that we can tweak. Then when developers use the model, they have.
You mean some denoising developers still have to tweaking a lot of the tweaking or some?
No, I mean, in this case, when developers integrate the Ray Reconstruction, they don't really change the model. They would sometimes have to tweak the renderer, but it's on our side to really tweak the model.
Yes, so my second question is, I'm not sure you can answer, so maybe, what is the DLSS roadmap or next step, or some, is there any plan for the next to do?
I can't comment on future products.
Okay, I see. Okay, thank you. So maybe thank you for attention. So you have been a great audience. So thank you.
Yeah, thank you for calling that.